So, we have looked at a few different number systems, such as the integers modulo n, and finite fields, and various extensions of the rationals. Today we will focus on the integers modulo n and gain a deeper understanding of how these work by probing these number systems with what we call point counting. Point counting is quite simple on the surface. We are just looking at how many solutions an equation has in the system we are studying. Since the integers modulo n are a finite ring, meaning that there aren't an infinite number of elements, we are guaranteed to get a finite number of solutions. Point counting is simply recording this number for all the rings we are looking at. The first implication we do is to look at the zeros instead of looking at solutions. A solution of f equal to g is just the same as the solution to f minus g equals 0, which is just the same as a 0 to f minus g. The second simplification we do is to limit ourselves to looking just at polynomials with integers coefficient. A polynomial with integer coefficients is anything you can get by adding, multiplying and subtracting integers and variables such as x and y. It is important to keep in mind the number of variables, and in this video we will be focusing on a special polynomial with two variables, namely x times y minus 1. So let's point count. First, in this first block of code, we define a function f which takes in an x and a y and returns x times y minus 1. Let's run this code. In this next block of code, we define a function point count which takes in a modulus and will return the amount of solutions to the polynomial in set modulo that number. First, we define a count variable which begins at 0. Then we loop through all the x's, then all the y's. And if f of x comma y, which is x times y minus 1, modulo the modulus is equal to 0, then we add 1 to the count. Finally, we return the count, which now holds all the number of solutions. Let's run this code. In this final code, we loop through all the numbers from 1 to 25 and call that number the modulus, and then we point count in that modulus. When we run this code, we will get all the point counts. Let's run it. Yes, this is it! We can see this first point count, which is for set modulo 1, the second point count, which is for set modulo 2, and so on. So, we have this weird sequence of integers and we don't know what to do with it. Well, there's a great resource on the internet called OEIS, O-E-I-S, which allows you to search for integer sequences. So, let's copy all of this, paste it into the OEIS, and let's search. Yes, this is the Euler totient function. So, we can see that we got the Euler totient function, also called phi. Let's try to understand what this function is. This function belongs to a very important class of functions called the multiplicative functions. A multiplicative function is a function that takes as input a natural number, so a number from 1 and onward, and spits out a real number, or a complex number if you know those. Further than just this, it has to satisfy a special condition. Whenever a and b are co-prime, meaning that they have no common factors, the multiplicative function f needs to be such that f of a times b equals f of a times f of b. So for instance, f of 6 must be equal to f of 2 times f of 3, but f of 8 doesn't need to be f of 2 times f of 4, because 2 and 4 have 2 as a common factor. The Euler totient function, or phi, is defined as follows. On the input n, it will spit out the number of integers from 1 to n, such that the integer is co-prime to n. For instance, phi of 9 is 6 because the 6 numbers 1, 2, 4, 5, 7, 8 share no common factors with 9, while 3, 6 and 9 do. Phi of 6 is 2 because 1 and 5 share no common factors with 6, but 2, 3, 4 and 6 do. Phi of 2 is 1 and phi of 3 is 2. Note that phi of 6 is equal to phi of 2 times phi of 3, which we would expect from a multiplicative function. It is not immediately obvious that it is multiplicative. This is something we need to prove. We won't do this in this video because it can get quite complicated. So why did we get the Euler totient function? What does it have to do with point counting? Well, let's look closer at what we counted. We counted the zeros of x times y minus 1. Well, this is the same as solutions to x times y equal 1. We can imagine that we divide both sides by y and get x equal 1 over y, And we see that what we are really counting is how many elements in the integers modulo n have a multiplicative inverse. Still, what does this have to do with the Euler totient function? Well, a first observation is that we are looking at numbers from 1 to n, which are exactly the numbers we look at in the integers modulo n. So let's say that the Euler totient function counts the elements in the integers modulo n that are coprime to n. So a conjecture here would be that being coprime with n is the same as being invertible modulo n. This makes sense, because for instance 2 shares common factors with 4, and it's not invertible. There is no integer I can multiply 2 with to get 1 modulo 4. This conjecture actually turns out to be true. Let's attempt to prove this conjecture. We start with seeing that a number a sharing common factors with n is equivalent to there being some non-zero number b, such that a times b is n. Well, modulo n is 0, so we get that a times b equals 0. If a were invertible, we could divide both sides by a and get b equals 0, but b was non-zero, so therefore a cannot be invertible. We still need to prove that a is invertible given that a is coprime to n. We will do this using Euler's theorem, which says that if a has no common factors with n, then a raised to the power of phi of n is 1 modulo n. If we let b equal a raised to the power of phi of n minus 1, then we get that a times b is 1, and that a is invertible. So we have a correspondence between numbers that are coprime to n and numbers that are invertible modulo n. And this shows us exactly why we got phi. A good question to ask is if we always get multiplicative functions when we point count in the integers modulo n. Let's explore this a bit. Let's say x of set modulo n is the number of zeros to the polynomial system x in the number system set modulo n. That is the integers modulo n. If we were to always get a multiplicative function, then x of set modulo nm would have to be equal to x of set modulo n times x of set modulo m, whenever n and m are coprime. So what is the relationship between set modulo nm and set modulo n and set modulo m? Well, the Chinese remainder theorem says that set modulo nm is isomorphic to the product of set modulo n and set modulo m if m and m are coprime. The product of two rings is simply the ring of pairs of one element from the first ring and one element from the second one. This isomorphism means that the numbers in set modulo nm correspond one-to-one with pairs of one number in set modulo n and one in set modulo m, and that this correspondence completely respects the structure of the rings. This means that the number of solutions in set modulo nm is the same as the number of solutions in set modulo n times set modulo m. So let's think about x of set modulo n times set modulo m. If x was the equation xy minus 1 equals 0, then in set modulo m, n times set modulo m, this becomes ab times cd minus 1, 1 equals 0, 0. We can simplify this to ac minus 1, bd minus 1 equals 0, 0. For the two pairs to be equal, the components have to be equal. So we get the two equations ac minus 1 equals 0 and bd minus 1 equals 0, where the first is an equation in set modulo n and the second is an equation in set modulo m. This is exactly what a solution of the equation in set modulo n times set modulo m is, a pair of solutions, one in set modulo n and one in set modulo m. If we were to count the number of solutions, this is just the same as the product of the amount of solutions in set modulo n and set modulo m. This example generalizes, and we always get that x of set modulo n times set modulo m, which is the same as x of set modulo nm, is just set of x modulo n times x of set modulo m. So this means we always get a multiplicative functions when we point count over set modulo n. Thank you for the attention. I hope you learned something, and leave a comment if you have any questions. Subscribe if you want to see more of this kind of content, and I hope to see you again.